Okay, hello. My camera wasn't attached, so the character wasn't moving. Good morning, good afternoon, good evening, whatever time of day it is. We are here, finally. It's been 2 days, which is longer than the usual. We took our first break, and I must say I didn't do anything good. So next time I should try to do better. But rest is needed sometimes. Okay, I wanted to tweet about this just for once before I actually start, in case anyone on Twitter wants to join. And then we will start taking the link of, where is the link? Share. Oh, shoot. Okay, let's say we're live. Hopefully there won't be any issues. Okay. How have you been? It's been a while. Let's see. Let's start with a recap. So, yep, you can see my screen. So, we were, yes, we are in lesson 6, and we were looking at, I think, different types of data products, like models you could work on, share, sell. This is what we were looking at, and then when the guy started being practical, we stopped the video. So we are exactly here. Let's refresh this and start.
I think what we might do then is take a break, and we're going to come back and...
Really? Searching for a new job? Now that's not easy. I wish you the best. I'm mostly worried about getting an answer for the PhD that I applied for. Yeah. Otherwise, everything is going well. Yeah, so they're taking a break.
And talk about these random forest interpretation techniques and do a bit of a review. So let's come back at 2 o'clock. So let's have a go at talking about these different random forest interpretation methods, having talked about like why they're important. So let's now remind ourselves like what they are. So I'm going to let you folks have a go. So let's start with confidence based on tree variance. So can one of you tell me one or more of the following things about confidence based on tree variance?
So he's asking us to review last things, because this is still lesson 2. I remember a lot about feature importance, but less on this.
What does it tell us? Why would we be interested in that? And how is it calculated? This is going back a ways, because it was the first one we looked at. Even if you're not sure, or you only know a little piece of it, give us your piece and we'll build on it together.
I think
Give me peace or give me war. Give me your peace.
I got a piece of it. It's getting the variance of our predictions from random forests.
That's true. That's the how. Can you be more specific? So what is it, the variance of?
I think it's, if I'm remembering correctly, I think it's just the overall prediction.
The variance of the predictions of the trees, yes. So normally the prediction is just the average. This is the variance of the trees.
And so it kind of just gives you an idea of how much your prediction is going to vary. So if maybe you want to minimize variance, maybe that's your goal for whatever reason that could be.
That's not so much the reason. So I like your calculation description. Let's see if somebody else can tell us how you might use that. It's okay if you're not sure. Yeah, have a start.
Does this have anything to do with the mean variance? That was the thing we worked on, isn't it?
So I remember that we talked about kind of the independence of the trees, and so maybe something about if the variance of the trees is high or low, then if,
no, not so much that. That's an interesting question, but it's not what we're going to see here. Do you want to pass it back behind you? So to remind you, just to fill in a detail here, what we generally do here is we take just one row, like one observation often, and like find out how confident we are about that, like how much variance.
Yeah, I think we forget, which is normal. But was it? I doubt that was before feature importance, but I do remember him taking one column, which here he took enclosure, and we looked at, I'm not sure what we were looking at exactly, but we looked at each value. So like these are different values within enclosure, and we said we don't even know what these are, but this is prediction, variance, something. Yeah. So we said this is more important, because then later on we realized, okay, this is enclosed vehicles that have ACs. These may not have AC.
There are in the trees for that, or we can do it as we did here for different groups.
According to me, the idea is like for each row, we calculate the standard deviation that we get from the random forest model, and then maybe group according to different variables or predictors, and see for which particular predictor the standard deviation is high, and then go deep down as why it is happening. Maybe it is because a particular category of that variable has very less number of observations.
Yeah, that's great. So that would be one approach. Is kind of what we've done here is to say, like, is there any groups that have that where we're very unconfident? Something that I think is even more important would be when you're using this like operationally, right? Let's say you're doing a credit decisioning algorithm. So we're trying to say like, okay, is Jeremy a good risk or a bad risk? Should we loan him $1 million? And the random forest says, I think he's a good risk, but I'm not at all confident. In which case we might say, okay, maybe I shouldn't give him $1 million.
But here? Confidence level here? Or overall?
Or else if the random forest said, I think he's a good risk, I am very sure of that, then we're much more comfortable giving him $1 million, right? And I'm a very good risk, so feel free to give me $1 million. Right? I checked the random forest before, a different notebook, not a
He's really cute.
So like this is like it's quite hard for me to give you folks direct experience with this kind of like single observation interpretation stuff, because it's really like the kind of stuff that you actually need to be putting out to the front line. Do you know what I mean? Like, it's not something which you can really use so much in a kind of Kaggle context, but it's more like, okay, if you're actually putting out some algorithm which is making like big decisions that could cost a lot of money, you probably don't so much care about.
They should also give us $500,000. Like, we don't mind.
The average prediction of the random forest, but maybe you actually care about like the average minus a couple of standard deviations. You know, like what's the kind of worst case prediction? And so, as Shikar mentioned, it's like maybe there's a whole group that we're kind of unconfident about. So yeah, so that's confidence based on tree variance. All right. Who wants to have a go at answering feature importance? What is it? Why is it interesting? How do we calculate it? Or any subset thereof? Dina?
Yes, maybe. Let me try before they go. So for feature importance, we did one hot encoding, and I mean, you can also not do one hot encoding, but doing it makes it, I think somewhere around here we did that. And you it's not the thing we did with the partial depend. Oh shoot, why am I forgetting things? Okay, give me a second. How do you calculate each importance of each feature being columns is you do you take it out as target? I don't think so. Shoot, I forgot. Okay, this proves that I do zero studying outside of these streams. Now I feel really bad, but I just know that feature importance is important, and you know, you can copy and paste the code and use it, but I forgot the how. Did you guys also forget?
I think it's like it's basically to find out which features are important for your model.
I know why. Obviously, we want to know which feature is improving our model and which one is just extra data that we remove. But I forgot the how.
So you take each feature and you like randomly sample all the values.
You have to check its correlation with the target. She's saying randomly sample. Let's see.
The feature, and you see how the predictions are. If it's very different, it means that that feature was actually important. Else, if it's fine to take any random values for that feature, it means that probably it's not very important.
Okay, that was terrific. There's this. That was all exactly right. There was some details that maybe were skimmed over a little bit. I wonder if anybody else wants to jump into like a more detailed description of how it's calculated. Because I know this morning some people were not quite sure. Is there anybody who's like not quite sure, maybe who wants to like have a go? Or
Me.
Want to just put it next to you there? Let's see. How exactly do we calculate feature importance for a particular feature?
So I think after you're done building the random forest model, you take each column and randomly shuffle it and generate a prediction and check the validation score. If it gets pretty bad for after shuffling one of the columns, that means that column was important. So that has higher importance. I'm not exactly sure how we quantify the feature importance.
Okay, great. Dina, do you know how we quantify the feature importance? That was a great description.
I think we take the difference in the square.
Or score of some sort, exactly. Yeah, so let's say we've got our dependent variable, which is price, right? And there's a bunch of independent variables, including year made, right? And so we basically, we use the whole lot to build a random forest, right? And then that gives us our predictions, right? And so then we can, let's call this y, right? And so then we can compare that to get, I don't know, whatever, R squared, RMSE, whatever you're interested in, right, from the model. Now, the key thing here is I don't want to have to retrain my whole random forest. That's kind of slow and boring, right? So using the existing random forest, how can I figure out how important year made was, right? And so the suggestion was, let's randomly shuffle the whole column.
Okay.
Right? So now that column is totally useless. It's got the same mean, same...
So the shuffle thing was for feature importance? I thought we did it for another thing. And I remember the question being asked, why do the shuffle? And he said, so that we don't have to retrain our model. Which is, he's saying the same thing right now. Okay, and I'm just repeating what he's saying.
Distribution, everything about it is the same, but there's no connection at all between particular people, actual year made, and what's now in that column. I've randomly shuffled it. Okay? And so now I put that new version through with the same random forest, so there's no retraining done.
They should be strongly correlated, either positively or negatively, otherwise it won't be a strong importance in the prediction process. I thought they did that to avoid overfitting the model, relying on that column only. I don't think it was that, because they're not going to retrain the model. I think it's just good to know that this technique is used for, variable importance. Yes, they're not retraining the model after that, but I do remember something close to, I think they were just removing a column and then retraining. And then we also did the partial dependence thing where we are just updating the value of a column. Like, do you remember we made it all like it was a year thing, so 1960, 1970. So that was also a technique that he used. I keep saying we, even though I did nothing.
To get some new y hat, I call it y hat ym, right? And then I can compare that to my actuals to get like an RMSE ym, right? And so now I can start to create a little table. So now I can create a little table where I've basically got like the original here, RMSE, and then I've got with year made scrambled. So this one had an RMSE of like 3, this one had an RMSE of like 2, enclosure, scrambling that had a RMSE of like 2.5, right? And so then I just take these differences. So I'd say year made, the importance is 1. 3 minus 2. Enclosure is 0.5, 3 minus 2.5, and so forth, right? So how much worse did my model get after I shuffled that variable? Does anybody have any questions about that? Can you pass that to Danielle, please?
I assume you just chose those numbers randomly, but my question, I guess, is, do all of them theoretically come out a perfect model to start out with? Like, will all the importances sum to 1, or is that not?
No.
They're just...
Honestly, I've never actually looked at what the units are, so I'm actually not quite sure.
Okay.
Sorry. We can check it out during the week. If somebody's interested, have a look at this sklearn code and see exactly what those units of measure are, because I've never bothered to check. Although I don't check like the units of measure specifically, what I do check is the relative importance. And so like here's an example. So rather than just saying like what are the top 10, yesterday one of the practicum students asked me about a feature importance where they said like, oh, I think these 3 are important. And I pointed out that the top one was 1,000 times more important than the second one. right? So like look at the relative numbers here. And so in that case, it's like, no, don't look at the top 3. Look at the one that's 1,000 times more important and ignore all the rest.
Okay. Find the ones that are really important.
Right? And so this is where sometimes the kind of your natural tendency to want to be like precise and careful, you need to override that and be very practical. It's like, okay, this thing's 1,000 times more important. Don't spend any time on anything else, right? So then you can go and talk to the manager of your project and say like, okay, this thing's 1,000 times more important. And then they might say, oh, that was a mistake. It shouldn't have been in there. We don't actually have that information at the decision time. Or,
oh yeah, I think there was a case where not adding data was a feature that was important, but like he said, it wasn't data that they had at decision time. So yes.
you know, for whatever reason, we can't actually use that variable, and so then you could remove it and have a look. Or they might say, gosh, I had no idea that like that was by far more important than everything else put together. So let's forget this random forest thing and just focus on like understanding how we can better collect that one variable and better use that one variable. So that's like something which comes up quite a lot. And actually another place that came up just yesterday, again, another practicum student asked me, hey, I'm doing this medical diagnostics project, and my R squared is 0.95 for a disease which I was told is very hard to diagnose. You know, is this random forest a genius or is something going wrong? And I said, remember, the second thing you do after you build a random forest is to do feature importance. So do feature importance, and what you'll probably find is that the top column is something that shouldn't be there. And so that's what happened. He came back.
Could be like ID for some reason, which shouldn't make sense. Just like here, ID is important, but it shouldn't be.
Half an hour later, he said, yeah, I did the feature importance. You were right. The top column was basically something that was another encoding of the dependent variable. I've removed it. And now my R squared is negative 0.1. So.
Oh my God.
That's an improvement. Okay. The other thing I like to look at is this chart, right? Is to basically say, like, you know, where do kind of things flatten off in terms of like which ones should I be really focusing on? So that's the most important one, right? And so when I did credit scoring in telecommunications, I found there were 9 variables that basically predicted very accurately who was going to end up paying for their phone and who wasn't, and like apart from ending up with
these applications sometimes just feel weird, don't they? Like deciding on humans. I know a lot of machine learning models are used to make decisions on humans, but it still feels weird. So learning about ethics alongside learning about how to use these tools is absolutely necessary.
The model that saved them $3 billion a year in fraud and credit costs.
$3 billion a year, dude.
Also let them basically rejig their process so that they focused on collecting those 9 variables much better. All right. Who wants to do partial dependence?
I remember that one. This is the one where we were looking at the relationship. Wait, isn't that what you were discussing? The correlation, whether they're correlated or not. That's the one you were discussing. So I guess you answered that question. And if you remember the graph of the year and then having the average or the clusters, so changing to look at the correlation, but also when he was looking at a dip in the data, he was like, that shouldn't mean the price is getting lower, it can be different by time. Was that also part of partial dependence? Because we did PDP for year and price, but then we said, oh, it might not be exactly right, so we did the thing, I don't know what the technique is called, but like replacing there with one value multiple times. I don't know if that's also part of partial dependence or not, but yes.
This is an interesting one. Very important, but in some ways kind of tricky to think about.
I'll go ahead and try.
Yeah, please do.
So from my understanding of what partial dependence is that there's not always necessarily like a relationship between strictly the dependent variable and this independent variable that necessarily like is showing importance, but rather an interaction between two variables that are working together.
Something like this, right?
Yeah.
Where we're like, oh, that's weird. Like you'd expect this to be kind of flat and there's a weird pokey bit.
Yeah. And so this example, what we found was that it's not necessarily year made or when the sale was elapsed, but it's actually the age of the model. And so that is easier to just like to tell a like company, well, obviously your younger models are going to sell for more, and it's less about when the year was made.
Yeah, exactly. So let's come back to how we calculate this in a moment. But the first thing to realize is that the vast majority of the time, post your course here, when somebody shows you a chart, it'll be like a univariate chart. They'll just like grab the data from the database and they'll plot X against Y, and then managers have a tendency to want to like make a decision, right? So it'll be like, oh, there's this like drop off here, so we should like stop dealing in equipment made between 1990 and 1995 or whatever, right? And this is like a big problem because like real world data has lots of these interactions going on. So like, maybe there was a recession going on around the time that those things are being sold, or maybe around that time people were buying more of a different type of equipment or whatever, right? So generally what we actually want to know is, all other things being equal, what's the relationship between year made and sale price, right? Because like if you think about the drivetrain approach idea of like the levers, you really want a model that says, if I change this lever, how will it change my objective? Okay? And so it's by pulling them apart using partial dependence that you can say, okay, actually, this is the relationship between year made and sale price, all other things being equal. Right?
Yep.
So how do we calculate that?
So for the variable year made, for example, you're going to you keep every other variable constant, and then you're going to pass every single value of the year made and then train the model after that. So for every model, you're going to have the light blue for the values of it.
And as far as I remember, we were using a sample of 50K because our data was too much, and we are retraining the model here. So yeah, last time we weren't retraining the model in feature importance, but we are retraining the model here in the partial dependence part.
And the median is gonna be the yellow line up there.
Good. Okay. So let's try and draw that. So by leave everything else constant, what she means is leave them at whatever they are in the data set. So just like when we did feature importance, right, we're going to leave the rest of the data set as it is, and we're going to do partial dependence plot for year made. All right, so we've got all of these other rows of data that we'll just leave as they are. And so instead of randomly shuffling year made, instead what we're going to do is replace every single value with exactly the same thing. 1960. Okay? And just like before, we now pass that through our existing random forest, which we have not retrained or changed in any way, to get back out a set of predictions. Why 1960? Okay, and so then we can plot that on a chart. Year made, against partial dependence, 1960 here.
And then another one for the year.
Okay,
next
then we can
year.
do it for 1961, 2, 3, 4, 5, and so forth. Right? And so we can do that for
That would be prediction, right? That would be Y.
on average for all of them, or we could do it just for one of them. Right? And so when we do it for just one of them and we change its year made and pass that single thing through our model, that gives us one of these blue lines.
Yep.
Right? So each one of these blue lines is a single row as we change its year made from 1960 up till 2008. And so then we can just take the median of all of those blue lines to say, you know, on average, what's the relationship between year made and price, all other things being equal. So why is it that this works? Why is it that this process tells us the relationship between year made and price, all other things being equal? Well, maybe it's good to think about like a really simplified approach. A really simplified approach would say, what's the average auction? You know, what's the average sale date? What's the most common type of machine we sell? Which location do we mostly sell things? And like we could come up with a single row that represents the average auction.
The averagest of the average. Okay.
And then we could say, okay, let's run that row through the random forest, but replace its year made with 1960. And then do it again with 1961. And then do it again with 1962. And we could like plot, you know, those on our little chart, right? And that would give us a version of the relationship between year made and sale price,
But
all other things being equal, right? But what if, like, tractors looked like that, and backhoe loaders looked like that, right? Then taking the average one would hide the fact that there are these totally different relationships.
so that's why we're taking. Isn't this is mean? This isn't median.
Right? So instead, we basically say, okay, our data tells us what kinds of things we tend to sell and who we tend to sell them to and when we tend to sell them. So let's use that, right? So then we actually find out, like, for every blue line, like, here are actual examples of these relationships, right? And so then what we can do is, as well as plotting the median, is we can do a cluster analysis to find out, like, a few different shapes, right? And so
But we can't really like do detailed analytics on this chart, can we? Like, we don't know what this is, even though it's a cluster. Maybe there are like ways of hovering on it and showing other information, but we're not doing that, right?
you may find, in this case, they all look like pretty much different versions of the same thing with different slopes. So my main takeaway from this would be that the relationship between sale price and year is basically a straight line, right? And remember,
the dip isn't real because it's not. Yeah, this is a better correlation versus the one that has the dip.
but this was log of sale price, right? So this is actually showing us an exponential, and so this is where I would then like bring in the domain expertise, which is like, okay, things depreciate over time by a constant ratio, so therefore I would expect older stuff year made to have this exponential shape. So this is where, like I kind of mentioned, like at the very start of my machine learning project, I generally try to avoid using as much domain expertise as I can and let the data do the talking, right? So like one of the questions I got this morning was like, oh, if there's like a sale ID, a model ID, I should throw those away, right? Because they're just IDs. It's like, no.
Really?
Right? Don't assume anything about your data.
So don't throw it away before you do feature importance. Because like even now I think IDs are useless.
Right? Leave them in, and if they turn out to be super important predictors, you want to find out, why is that?
It can prove that your data isn't clean.
Okay, but now I'm at the other end of my project, right? I've done my feature importance. I've pulled out the stuff which is like, from that dendrogram, the kind of redundant features. I'm looking at the partial dependence, and now
Dendrogram.
I'm thinking like, okay, is this shape what I expected? Okay, so even better, before you plot this, first of all think, what shape would I expect this to be? Because it's always easy to justify to yourself after the fact, oh, I knew it looked like this. Right? So what shape do you expect? And then is it that shape? So in this case, I'd be like, yeah, this is what I would expect.
Okay.
Where
The ID might have an interesting things in it, not necessarily generated randomly. That is true. That's true. Sometimes IDs are like what is it called? Like shorter versions of the main data. So like it could be the year could be in the ID. Some types could be in the ID. You know what I mean, right?
Where else? This is definitely not what I'd expect. So the partial dependence plot has really pulled out the underlying truth. Okay. So does anybody have any questions about like why we use partial dependence or how we calculate it? Who's got the... Oh, you've got it.
I'm looking forward to the students' questions. They follow a pattern. Yeah, some of them are random, some of them are just serial numbers, and some of them are like substrings of different columns of the data. I mean, there are different types of IDs.
You found, say, 20 features that you think are important. Are you gonna measure the partial dependence for every single one of them? So is there a limit on that?
If there are 20 features that are important, then I will do the partial dependence for all of them. Where important means like it's a lever I can actually pull.
So we did partial dependence for the most important feature? But still, I doubt everything is as important. Like they may be close, which means they're correlated, but they may not be all as important. Like 20, that's way too much. There has to be some sort of issue, like you're collecting similar data. Date, week, day, whatever. Date, time.
It's like the magnitude of its size is like not much smaller than the other 19. Like, based on all of these things, it's like, yeah, it's a feature I ought to care about. Then I will want to know how it's related. It's pretty unusual to have that many features that are important both operationally and from a modeling point of view, in my experience.
Sorry, one follow-up.
Sure.
How do you define important actually, now that I think about it?
So important means it's a lever, so it's something I can change. And it's like, kind of at the spiky end of this tail. Or, maybe it's not a lever directly, like maybe it's like zip code, and I can't actually tell my customers where to live, but I could like focus my new marketing attention on a different zip code,
Would it make sense to do pairwise shuffling for every combination of two features and hold everything else constant, like in feature importance, to see interactions and compare scores?
So you wouldn't do that so much for partial dependence. I think your question is really getting to the question of could we do that for feature importance? Right? So I think interaction feature importance is a very important and interesting question. But doing it by randomly shuffling every pair of columns, if you've got 100 columns, sounds computationally intensive, possibly infeasible. So what I'm going to...
Oh, okay, he's going to answer. Okay. But like, wouldn't we have removed some features? Having data with like a lot of columns, yeah, that is computationally expensive. And now I'm repeating what he's saying again. I'm just, trying to put it into my brain. That's why I keep repeating what he's saying. I feel like I'm boring you guys to death.
What I'm going to do is, after we talk about tree interpreter, I'll talk about an interesting but largely unexplored approach that will probably work. Okay, who wants to do tree interpreter? All right, over here, Prince.
Did we look at one row in tree interpreter? Did we?
Can you pass that over here to Prince?
I was thinking this to be more like feature importance, but feature importance is for complete random forest model, and this tree interpreter is for feature importance for particular observation. So
we were... Wait, I remember. We did it on an Excel sheet. We looked at one... We even looked at... Did we look at the one tree? One tree. And then we looked at the decisions, and we looked at the mean RMSE, I think. And then we plotted that.
if that, let's say it's about hospital readmission, so if a patient A1 is going to be readmitted to a hospital, which feature for that particular patient is going to impact, and how can we change that? And it is calculated starting from the prediction of mean, then seeing how each feature is changing the behavior of that particular patient.
I'm smiling because that was one of the best examples of technical communication I've heard in a long time. So it's really good to think about, like, why was that effective, right? So what Prince did there was he used as specific an example as possible. Mm-hmm. Right? So humans are much less good at understanding abstractions, right? So if you kind of say, oh, it takes some kind of feature, and then there's an observation in that feature where it's like, no, it's a hospital readmission, okay? And so we take a specific example. The other thing he did, which was very effective, was to kind of take an analogy to something we already understand. So we already understand the idea of feature importance across all of the rows in a data set.
Yeah.
So now we're going to do it for a single row. Okay. Mm-hmm. So one of the things I was really hoping we would learn from this experience is how to become effective technical communicators.
Something that I'm extremely bad at. Like I'm out here trying to explain things, but I'm not doing it well. Which sometimes I hope my, inability makes you guys curious to learn more. I don't know.
So that was a really great role model from Prince of using all of the tricks that we have at our disposal for effective technical communication. So hopefully you found that.
You're just saying that to make me feel better. But thank you.
A useful explanation. I don't have a hell of a lot to add to that other than to show you, what that looks like. So with the tree interpreter, we picked out a...
See, we selected. You're better than most of my uni professors, at least. Okay, that is making me feel better, but yeah. But that's also making me sad. Well, I've had university lecturers that it felt like they were, just mumbling. They weren't even talking. So yes, there are a lot of people who have bad communication skills that are lectures. And that's, I mean, I feel like I don't know, it's like you have a degree, now go teach. It's not really supposed to be like that, but why? Why for what? Yeah. It's supposed to be, I think in my country it's getting better because there are like tests and like pedagogical things, but the why it's making me sad. Now I get it. Because they should not, like, there should be, I'm not saying they shouldn't teach, I'm saying they should be given tools to make them better communicators, because they're probably smart people. Some people are good in research, super bad at teaching. Yeah, exactly. Yes. And that makes students suffer. Yeah. I hope we can break this cycle. If we become teachers or lecturers, I hope we can do better for our students. Like Jeremy Howard is an extremely amazing one. I asked why my comment made you sad. Yeah. Yeah, no worries. I talk. Yeah. He's like fun instructor, but also like engaging and helps you understand. And the fact that now he's making us a review and questioning our own understanding of the past lectures, I suppose. I'm like, yep, that's he's literally using a full lecture's time to review the students. Who does that? Yeah. More reason to love him.
Row. Okay. And so remember when we talked about the confidence intervals at the very start, the confidence based on tree variance, we mainly said like you'd probably mainly use that for a row. So this would also be for a row. So it's like, okay, why is this patient likely to be readmitted? Okay, so here is all of the information we have about that patient.
He actually gave us that example last time. Needing to do some scans, something like that. I used YouTube extensively to fill in my knowledge gaps when I was a student, and here I'm still using it to learn new things after finishing uni. Yeah, same here actually. I don't think you're the only one. It's yeah, like when I was in high school, I say I wasn't using the internet to understand things, but after like uni and all that, it's now become a tool that we need to use. Either it's knowledge gaps or trying to get ahead, It's a tool that is available, so why not use it? But yeah, using it for filling knowledge gaps. I mean, even I wouldn't say it's a bad thing if it helps you understand better, but also the knowledge gaps shouldn't be at a place where you can't even connect the dots. Like, there needs to be gaps so that you're curious and you get to learn more. But it should, because I don't think teachers should give you everything on a silver platter. That makes you lazy. But they shouldn't make you like hungry to the point of starving. I'm using analogies.
Patient, or in this case, this auction. Right? Why is this auction so expensive? So then we call treeinterpreter.predict, and we get back the prediction of the price, right? The bias, which is the root of the tree. So this is just the average price for everybody. So this is always going to be the same. And then the contributions, which is how important is each of these things, right?
These things being reverse classroom model. I don't think I know that. The reverse classroom model. Maybe like you're saying that the students teach the teacher? That is that? Okay, maybe. Yeah. This is feature name and this is feature, the column that we are looking at, and how they're contributing to the prediction, right? Because we're looking at one row.
And so the way we calculated that was to say, okay, at the very start, the average price was 10, right? And then we split on enclosure, right? And for those with this enclosure, the average was 9.5. And then we split on year made, I don't know, less than 1990. And for those with that year made, the average price was 9.7.
Yeah, making students reach the information. Instead of giving it, the teacher's role is to guide them. Instead of giving them on a silver platter. Okay, I see. Silver plate, yeah. I didn't know it had a name, but yes. Okay. Guiding instead of giving them answers. Yeah, that's a good model. It may not be as easy to do in a big class of like 30 people, but we should still try.
Right, and then we split on the number of hours on the meter, and for with this branch we got 9.4. Right, and so we then have a particular option which we pass it through the tree, and it just so happens that it takes this path. Right, so one row can only have one path through the tree.
Fair.
Right, and so we ended up at this point. Okay, so then we can create a little table, right? And so as we go through, we start at the top, and we start with 10, right? That's our bias. And when we said enclosure resulted in a change from 10 to 9.5, minus 0.5. Year made changed it from 9.5 to 9.7, so
minus
plus
3.
0.2.
Oh,
right?
wait.
And then meter.
Wait. So you're doing a rolling thing? I thought it would be here. It's 3 from 10, so it'd be minus. We're doing the value from.
I changed it from 9.
Isn't that a bit confusing?
0.7 down to 9.4.
I remember him saying we do a total of these values, and that's like the average,
which is minus 0.3. And then if we add all that together, 10 minus a half is 9.5, plus 0.2 is 9.7, minus 0.3 is 9.4.
It's the final value that we get, not average. I see.
Lo and behold, that's that number. Which takes us to our Excel spreadsheet. Where's Chris, who did our waterfall? There you are. All right, so last week we had to use Excel for this because there isn't a good Python library for doing.
No way did that guy create the Python library that he asked for.
Waterfall charts. And so we got our starting point, this is the bias, and then we had each.
Like, all I can say is mashallah to these students. They're bachelor students.
Each of our contributions, and we ended up with our total. The world is now a better place because Chris has created a Python waterfall chart module for us and put it on pip. So never again will we have to use Excel for this. And I wanted to point
This is the sweetest thing.
out that, like, waterfall charts have been very important in business communications at least as long as I've been in business. So that's about 25 years.
Wow.
Python is, a couple of decades old, a little bit less. Maybe a couple of decades old. But, despite that, no one in the Python world ever got to the point where they actually thought, I'm going to make a waterfall chart. So they didn't exist until 2 days ago. Which is to say, the world is full of stuff which ought to exist and doesn't.
Yeah, finding the gap.
And doesn't necessarily take a hell of a lot of time to build. Chris, how long did it take you to build the first Python waterfall chart?
Disclaimer is that the code is the...
Well, there was a gist of it, yeah.
But it wasn't a function.
Yeah.
And
Yeah. About 8 hours. Okay, so, a hefty time amount, but not unreasonable. And now, forevermore, people, when they want the Python waterfall chart, will end up at Chris's GitHub repo and hopefully find lots of other USF contributors who have made it even better.
Wow.
So
That's
in order
amazing.
for you to help improve Chris's Python waterfall, you need to know how to do that, right? And so you're going to need to submit a pull request. Life becomes very easy for submitting pull requests if you use something called Hub. So if you go to GitHub/Hub, that will send you over
GitHub Hub? I haven't heard of that.
here. And what they suggest you do is that you alias Git to Hub, because it turns out that Hub actually is a strict superset of Git. But what it lets you do is you can go Git fork, Git push, Git pull request, and you've now sent Chris a pull request. Without Hub, this is actually a pain and requires going to the website and filling in forms and stuff, right? Okay. So this gives you no reason not to do pull requests. And I mention this because
Yeah. This teacher has a lot of good tools up his sleeve.
When you're interviewing for a job or whatever, I can promise you that the person you're talking to will check your GitHub. And if they see you have a history of submitting thoughtful pull requests that are accepted to interesting libraries, that looks great, right? It looks great because it shows you're somebody who actually contributes. It also shows that if they're being accepted, that you know how to create code that fits with people's coding standards, has appropriate documentation, passes their tests and coverage, and so forth, right? So when people look at you and they say, oh, here's somebody with a history of successfully contributing accepted pull requests to open source libraries, that's a great part of your portfolio.
True.
Okay? And you can specifically refer to it, right? So either I'm the person who built Python waterfall, here is my repo, or I'm the person who contributed currency number formatting to Python waterfall, here's my pull request. Anytime you see something that doesn't work right in any open source software you use is not a problem. It's a great opportunity.
Yeah.
Right? Because you can fix it and send in the pull request. So yeah, give it a go. It actually feels great the first time you have a pull request accepted. And of course,
I don't think I've ever done it to something that is not a part of actual work. I've never done it on open source tools or libraries.
One big opportunity is the fast.ai library. And thank you. Who was the person here, the person who added all the docs to fast.ai structured? In the other class. Okay. So thanks to one of our students, we now have doc strings for most of the fast.ai.structured library. And that, again, came via a pull request. So thank you. Okay. Does anybody have any questions about how to calculate any of these random?
Still. That's cool. I've never been brave enough. You've been brave. We'll think about it.
Forest interpretation methods, or why we might want to use any of these random forest interpretation methods. 'Cause towards the end of the week, you're going to need to be able to build all of these yourself from scratch.
Ooh.
One over there.
I mean, from scratch, or having this, right? I think he said it will be open book. Not that I'm participating.
Can you pass that, please? That's right.
Just looking at the tree interpreter, I noticed that some of the values are NaNs. How I get why you would keep them in the tree, but how can an NaN have a feature importance?
Okay, let me pass it back to you. Why not? So, in other words, how is NaN handled in pandas and therefore in the tree?
Set to some default value.
Does anybody remember how pandas, notice these are all in categorical variables. How does pandas handle NaNs in categorical variables, and how does fast.ai deal with them? Can somebody pass it to the person who's talking?
-1 for pandas?
Yeah, pandas sets them to -1 category code.
Yeah.
And do you happen to remember what we then do? Doesn't matter really. We add 1 to all of the category codes.
0?
So it ends up being 0.
Yeah.
So in other words, we have a category with, remember, by the time it hits the random forest, it's just a number, and it's just the number 0, right? And we map it back to the descriptions back here. So the question really is, why shouldn't the random forest be able to split on 0? It's just another number.
True, but also like knowing that NaNs are important in your model makes you understand, shows you like issues or things about your model. So I don't think it should be removed or not be able to be split on.
So it could be NaN, high, medium, or low, 0, 1, 2, 3, 4. And so, missing values are one of these things that are generally taught really badly. Like often people get taught, like, here are some ways to remove columns with missing values or remove rows with missing values or to replace missing values. That's like never what we want, because missingness is very, very, very often interesting. And so we actually learnt that from our feature importance that coupler system NaN is like one of the most important features. And so for some reason, I could guess, right? Coupler system NaN presumably means this is a kind of industrial equipment that doesn't have a coupler system. Now, I don't know what kind that is, but apparently it's a more expensive kind.
Ah.
Does that make sense?
Yeah.
Okay. So, yeah, I did this competition for university grant research success, where by far the most important predictors were whether or not some of the fields were null. And it turned out that this was data leakage, that these fields only got filled in most of the time after a research grant was accepted.
Yes, right? He discussed that last time as well.
Right? So, it allowed me to win that Kaggle competition, but didn't actually help the university very much. Okay, great. So let's talk about extrapolation.
I'd love to. I would really love to, but I think my time's up. I've been streaming for over an hour and 15 minutes. And I'm looking at the video and there's like 20 minutes left, and I'm like, for the next stream, would that be too little? Yeah, this is today. I think there was some glitchy bad frame rates, but there wasn't any cuts, so it's not great, not the worst. Thank you for being here. This was a review lesson, so that was fun. I like the fact that it was a review lesson to remind us and get our understanding. Thank you for tuning into the stream, for talking to me, for, some YouTuber stuff like liking and subscribing and all that. I've been getting a lot of engagement for the past almost 3 weeks now, so it's nice of you guys. You don't have to, so I appreciate that. No cuts, some lags from my part, but good, all things considered. Yeah, there seem to be lags and really? Shoot. What do you mean? Oh, I thought it's an error. Yeah. Actually, that window thing I added because I thought it makes it look better. This is what it looked like before. I like the window more. It makes it more, homey. But yeah, it looks creepy now. I think, I was actually thinking of updating my background. I really like it. It makes it look like I'm sitting at a window, but I can have the thing behind the window change because the texts up here are written on the picture, but I should have a way where instead of having it I suppose, it's an Easter egg. Instead of having it be written on the picture, it should be written somewhere around my template thing. Okay. I was also thinking of having some alerts, because Twitch allows alerts for followers and things like that, but I wasn't sure how to add it here, so I will look into that, because I think it will be fun to see when I get likes or subscribers. If I can have alerts for that would be fun. Okay, I should go. In a weird way, I missed streaming, because it makes me feel like I'm doing something good for my brain and hopefully helping some few people. Thank you for being here. Thank you for your time and energy. I hope you have a lovely rest of your day. It's Wednesday, isn't it? Yep. So weekend is near. That's lovely. I'm going to end the stream starting from 10. If there's anything, let me know. Otherwise, enjoy the rest of your day. So ending the stream in 10, 9, 8, 7, 6, 5, 4, 3, we go 2. Yep, Wednesday. Thank you for your energy too. And 1. I think there's a lag. Lift off, starting the day. Bye. Thanks.